Please. Okay, so sorry for the delay. It's my fault, but still something to organize at the last minute. Okay, so this is the title is how macro models micro, and conversely, I'm going to explain it. And as I said yesterday, this talk should be a little more serious than yesterday. I mean, the talk was very serious yesterday, but it was with a few mathematics. Okay, so let me start by quoting a sentence by Jean Perrin. Jean Perrin was a French physicist. He got the Nobel Prize in 1909 or something like this, before having proved the existence of atoms. So it's a beautiful sentence. I just read in French the beginning. Il y a 25 siècles peut-être, sur les bords de la mer divine, où le chant des Aèdes venait à peine de s'éteindre, quelques philosophes enseignaient déjà que la matière changeante est faite de grains indestructibles en mouvement incessant. You have the translation here. Jean Perrin was a fascinating man. In fact, he discovered two very big things. First of all, he proved the existence of atom, and secondly, he proved the existence of CNRS, Centre National de la Recherche Scientifique, by creating it in 1939. I don't know which of the two is the most important, but for me the second was very important. CNRS was created in 1939. I think it's interesting also the date, because nowadays one has the habit of saying that nice things should be created in a peaceful period of history. So you see 1939 was not at all in Europe a peaceful part of history. So since I'm going to talk from micro, that is particle, molecules, whatever, to macro, that is to the situation at our scales, let me just point out 3 or 4 different Greeks. So Greece, as it was mentioned by Jean Perrin. There is something which is not so known, and I learned during my study at University. When Newton published and elaborated his theory, people were not very happy with the conception of action at distance, and we're still not very happy. I mean, we had basically to wait general relativity to get an explanation to the problem, why do the Earth attract Moon, and more precisely to see how Moon knows the distance between her and the Earth, right? So it was a competitive theory in Switzerland, in Geneva, which was stated by something else but formalized by François Lucien, I think, Le Sage, which was called theory of particules ultramondaines. Ultramondaine because one couldn't see them. They were supposed to be in another world, in which not our. And with this theory, you explain, for example, the attraction by saying that basically you have a flow of particles everywhere, and when you are in front of a planet, you have the shadow of the planet, and the shadow of the planet in the flow of particles gives you the attraction like this. It's a fascinating theory, and I remember in this lecture, in this course by Jean-Marc Lévy-Leblanc, that with the course he told us how can you disprove it. And you can explain, of course, not as simply as Newton did, but you can explain a lot of things. And in fact, the only true argument you had against this theory of particules ultramondaines was that that this particle would have destroyed the Apollo capsule in the space, because there would be too many particles. So, you know, before the 70s, basically, you couldn't unprove the particle ultramondaine by François Lesage. And I think it's interesting because it was a theory of particle in the large n limit also. Then, of course, Boltzmann. Let me remind you that I think Mario will talk about that tomorrow, but there were people against Boltzmann because Boltzmann were using the atomic hypothesis or molecular hypothesis. I want to quote Planck, who in 1900 created somehow the quantum mechanics, but in fact, a few years after, he was against, and he came back, and there is one of these paper, not one of these book, he said that, well, all that is very nice, but at one point, we will have to come back to the hypothesis of continuous matter. Even Planck was doubting on that. But the most funny part is, well, if you, the next one, That is, if you look at the cours de physique théorique at Sorbonne University, in the late 30s, the name of the course was Sur l'hypothèse atomique. So even at the beginning of the Second World War, atomic was just an hypothesis. So you see how long it was to really accept that macro systems are built out of micro particles. So I decided in this micro course, not short mini course, not to look at application, a lot of picture, but to try a little bit, as the contrary of yesterday, to concentrate on the methodology and to the mathematical object, although I want to give, of course, any proof. So the keys of I'm going to use in this talk, I have listed some of them here, like this. So trajectories, of course, it is a Lagrange view of particles. Loss of information, because we are going to take averaging over all particles but one, or but two, but three, but that is a loss of information. Probability, because I'm going to get rid of trajectory very quick and look to the Liouville equation instead of Newton equation. That is how to propagate densities, that is a probability measure by the flow. Probability on the space of n particles, and then probability on the space of one particle. Continuous measure, expectation, which is part of loss of information. Averaging, evolution, all what I'm going to tell you will consider a system of n particles in the limit when n goes to infinity. And of course, when you have n particles, if you look in a rough way to your system of n particles, when n tends to infinity, everything explodes because you don't have a framework, so you have to cook up some derivative quantities which have a limit themselves. So I give you the keys, now I give you the logs. What will be the logs? So, as I mentioned, I will put myself in a framework. I will explain this much more precisely. It's just a kind of introduction. Instead of trajectory, I will look, you know, when you have a flow, it's equivalent basically to look at the flow or to look at density. If you have a big set of density and look how density are pushed under the flow. So I will be in this kind of a framework. For specialists, this means that I will not consider empirical measure, but I will be on Euler's side, so to speak, of the theory. Density for n particles will mean that it's the evaluation of the density will be the probability that n particles occupied n given sites, the variable of the density on which you evaluate the density. Neglecting information about n minus 1 over n particle, and that's going to be the miracle. And I insist on this because usually you say, okay, this will be called the first marginal. The first marginal tends to the Vlasov equation, but there is a preliminary result. Is the fact that when you neglect information about n minus 1 particle over n, this quantity has a limit when n goes to infinity. Although the whole information about n particle just blows up and then diverges. One particle, so when neglecting n minus 1 over n means that remains one particle, and this one particle will be a witness of the n minus 1 others, and it will be described by the probability density, which will satisfy an equation very close to the Liouville equation, but this time non-linear, which means that we will have something like a theory of a particle interacting with herself, or with itself, let's say, with itself. Once again, I will explain all that. And self-interacting particles, that's what I was mentioning. And this, after all this pass, will something which will mimic continuous media. Okay, so let me give you quite a long overview about the different systems. That is now I'm going to incarnate it a little bit, what I just said now. I will drink something now. So my next slide is just something just to illustrate and to put some images, because otherwise I feel ridiculous. But I think about this theory of cells and the macroscopic limit of n cells when n diverges will be much better explained and shown by, in the talk by Marta Menchi in a little while. Question of scales. When you have a microscopic scale, cells or particle, whatever, you are something like the Newton law. And I will consider something from the beginning which is a little bit new in this kind of thing. That is, I will consider that the particles are coupled with at a chemical scale with a kind of chemical activity. And in a very explicit way I'm going to talk about. So if I make a resume of the different scales, I will be here with n particles. Under this, I have the chemical scale, which I will not consider as particles, but just as a continuous media interacting to a diffusion equation to the particles themselves. When n goes to infinity, I'm going to show you that when you neglect n minus 1 or n minus 2, etc., but not n minus 1, of course, I will get an equation on phase space which will be associated to the name of Vlasov and which will be a nonlinear equation. When you talk to, for example, to biologists or to doctors, they are not very happy with the phase space. Let me recall what means phase space. We know that in the Newton theory, the second order differential equation, the famous F equal m or in Italian, gamma in English, but in R, A in Italian. And of course, when you have a second order differential equation, you can always, by adding a first variable, which is the first derivative, reduce this to a system of first order derivative. And this means that the true space of a system of n particles interacting through the Newton law or generalization of Newton law is in fact a space of is a space considering of our physical space or 3 and the space of velocity, because you know that each trajectory is remembering the value of the velocity at mt. So of course, when you talk about space and velocity to people who are not mathematicians, they are confused because they see only our physical space. So there is a way of passing from this to this, which corresponds to passing from Vlasov to what we call Euler, and that Mario wouldn't like to call Euler, but I still call Euler. and prevent the questions. And I will explain you how you pass from here to here. And there is a last for biology things, but because here you pass from one function on phase space, that is space and velocity space, into two functions, one on the space, which is density, and the density of velocity again on the space, but which remembers the velocity. And there is a way in biology to get rid of this velocity, because once again, for people who are not mathematicians, a velocity field is something very abstract, and it's named by the name of Keller and Siegel. But I mentioned this, but I will not at all talk about that, because it doesn't fit yet in our program. Okay, so let me start. What's the Newton law? So you have a configuration space, that is our space. I'm a little bit snobbish by putting d equal 1, 2, 3, because it should be d equal 3, and or d, whatever, which number it is. And this is a Newton law. Acceleration times the mass is equal to the force. And this equation lives on the configuration space of n particle, which are the one of n particle times n times with itself, because we have one position for each particle. Okay, this gives rise to a trajectory in this space. It might not be a flow. In the case, for example, we have the interaction with a chemical background. I will explain you that. And by once again defining the velocity out of the first derivative, we get a system of first order differential equation. Maybe I should, yeah, no, right. Very soon d by dt will become dot, because it's a very practical notation, but I will mention when I will need this. And so in this lecture, what is going to force depend on? It could depend on time. That doesn't change so much. Of course, it depends on all the variables at the same time where you look as the derivative of the position, x1t, xnt, v1t, vnt. But I will consider a situation where it depends also on the whole trajectory before the time t. That is, it's not local in time, so to speak, it depends on all the trajectories. And I reduce myself to s smaller than t. I know one example where the dynamic depends on the trajectory for s bigger than t at time t. That is, depends on future. It's a situation where you all know, I'm going to try to relax you, it's just a mundial of football. You know that when the day before the final, you make what's called the small final, the winner of the small final is supposed to be the third in the classification, right? And this depends on the result of the second. Because since you imagine that you have two groups of people, if the winner, if the one who loses the final doesn't belong to the same group as the one who wins the small final, there is no reason to say that the second is before the third, if you think about it, because they never compete against. The ordering is totally broken. So I think it's a nice example, and it might be that there are some physical examples which are interesting and which depends on the future like this. But that is football. It's out of this hypothesis for some reasons and many others. So I think that this is exactly the frame of the paradigm on which we will be, and let me show you that it covers a lot of examples that I'm going to describe, and I will give you a unified approach for all the following examples. So the first one is two-body interaction. You remember that here I said that the force depends on everything. Now for the two-body, you imagine that the force for the particle J depends on the sum of all the other particles, but somewhat as a function of something which depends only on two particles. This is a very natural hypothesis in physics. I don't know why it's natural. It's a fact, because I remember even when I was student, which is many years ago, after Newton, but still many years ago, I asked to my teacher, but why isn't it a three-body interaction in physics? We could perfectly imagine that the interaction between the Earth, the Moon, and the Sun depends on the three particles to the three positions of the three planets and Sun. But it's not the case, so this is a famous ansatz, so to speak. And the natural ansatz is when this force, it derives that this is a gradient of potential which depends on the difference of the two. This will be broken very quickly, and the fact that it depends only on the difference will be also broken in the theory of adjoint systems that I'm going to show you a little bit later on. Okay, so some picture generously given by Marta. We all know that even if this function G is something very nice, you start by something very close like this, and then it disperses, and all the possibility of complicated dynamics can happen. Okay, so let me now show you an example which was related to what Stefano showed on Tuesday night, and he will develop better now. But this is the first example of dynamics where you see the derivative of the velocity doesn't depend only on the position, but depends also on the position and on the velocities themselves. And it's a model which has been introduced by Smale and Cooker and Smale, and which has the property that after a certain time, all the velocities are on the same direction, and this is exactly what Stefano showed you in the movies. You have all the birds which follow the same direction all the time. This flocking phenomenon. There is a reason, of course, for this, is because you see that if all the VI are the same, this is zero, and then you get a fixed point of your dynamics. But the converse is more difficult to prove, of course. Sorry?
So it's VI minus VJ?
VI minus VJ, yeah? Maybe there is misprint. You mean there is misprint?
Yeah, I think there is a minus.
Oh. Yeah, there is a minus. Yes, there is a minus, of course. Get tested, sorry. Okay. So there is a minus somewhere here. Okay. So the topological interaction is exactly what has been described, and that I think you're going to talk about in your talk, right? So I pass very quickly. Now, what about chemotaxis? Well, the chemotaxis is the following. You have a force here, which depends on the position, the difference of the position, difference of velocity. It could depend independently on the two, but we take it in the difference. And then we add a kind of, it looks like an external force in the sense that it depends only on the position. You see you have the same I here and the same I here. So it's a gradient of a function which depends on the point where you're looking at the velocity too. But this function itself satisfied a parabolic equation of this form, a diffusion equation, tells you that the derivative of phi of t is equal to Laplacian of phi minus a term like this that we could forget about for the moment, and then a sum of what? A sum of things which depends on the trajectories itself. You see, if you think about this, in fact, it's a fake notation to say that it depends only on xj, because it depends, in fact, through this equation, to all the history from t equals 0 to t equals t, that is to s equals 0 to s equals t, of all the particles, because here we have a sum of j. So it's a complicated stuff, and it breaks the Markovian property. That is, you have something where the dynamics at time t for one particle depends on all the particles for all the trajectory before the time t. Okay, and then the fifth example I want to tell you is something where you have to change the notation, but I will tell you immediately the difference. So you take a system, a differential equation, a system of differential equation like this. You have the, so now you stress me with your question. So you have I, which is in the index, you have n particles. I varies from, I should have written, from I equal 1 to n. And you have a sum of also a function depending on two particles, but this time, you see the difference that this function depends on the indices I and j. You see, when I wrote the two-body interaction, here j were not depending. It was the same function for all pairs of particles you were considering. Now, you suppose that your function, your dynamics, depends on each indices. That is, what you mean by this is that if you look at a two-body interaction like this, if you invert A and J, it doesn't change your dynamics. That is, you preserve indistinguishability of the particles. This one doesn't. It breaks this hypothesis because if you exchange things, you still have memory of the indices here. And this causes certain trouble because a lot of the part of the theory use this indistinguishable property. And of course, in the Boltzmann equation tomorrow, you're showing that it's absolutely fundamental. Nevertheless, of course, the interaction should depends on A and J. For example, you know that the interaction between Francesco and Mario depends on Francesco and Mario. It's the same if you replace Francesco and Mario by somebody else, right? No, you don't like it? No? Okay. Okay. So it's this system like this, you know, where the dynamics depending on the labeling of the particles, it's called opinion system, or agent system, multi-agent systems. There are a lot of definition, and one kind of example, emblematic example, is when you have something where you have that. Oh, sorry, there is a mistake here. Yeah, I forgot the backslash here. So this is xi in this sense here. So it depends only linearly on the difference of xi I minus xi j.
Ah, xi.
Yeah, sorry, it's a LaTeX mistake, right? But if you read it, it's the same, by the way.
Yeah.
And you see that the fact that it depends on the difference of the two unknown is just remembering exactly the case of Cooker's mail here. So these are systems which develop also a kind of flocking phenomenon that for agent system you call a consensus. That is, at one point, if you imagine that the value of Cj is an opinion of people, then after a while, everybody has the same opinion because you have a fixed point where all the opinions are the same. I think I will tell you now very briefly that the theory we are going to develop with this common work with Emmanuel Trella, we will put all that in a probabilistic framework, as I said at the beginning, that is pushing forward probability instead of looking at trajectory by trajectory. This means that, in fact, we are looking at the fact that each agent I doesn't have a precise opinion, but have a possibilities of opinion. And for example, if you look at in social sciences as people who are going to vote, it's exactly the case. You know, 1 hour before to vote, they don't know what they're going to vote, but probably they're going to vote for this one or this one, but it's not true. So this will be a new part of, I think, in this theory. Now, there is an example 5Bs, which will be the inverse way. You know, you remember in my title, I finished my long title with and conversely. So what do I mean by conversely? Well, you see, I mentioned that a way of handling this will consider neglecting all the particles but one and having a density of this. This means that, in fact, this neglected n-1 trajectory density will satisfy the nonlinear PDEs, which is called the Vlasov equation. Now, suppose you try to do the contrary. You take a PDE, your favorite PDE like this, and you wonder if this PDE could be the Vlasov equation of a certain system of particle system. That is, now you suppose that you know the limit equation, and you try to find a particle system which gives rise through this big N limit to your favorite PDE. And I will show you, forget about this terrible formula, that for some equation, and a lot of some equation, and we believe, for example, for all the quasi-linear PDEs, that is even non-linear PDE, it is a case, and you can build an approximation of your PDE as system of ODEs in the large N limit of the system.
Sorry, you should give me references of that.
Right now?
No.
Ah, okay.
You can't.
You will be over-satisfied by reference at the end. No, sure. I'm in the part of my talk called overview, still. Okay, no, but I will give you a reference, of course. I'm teasing you. But. Okay, so this is the last part, which will go from macro, that is a one-particle PDE, I mean a particle living in R3, basically, into micro, whose limit, when the micro involve more and more particles, give you the macro equation. Okay. So I have 20 minutes, okay. So what about the methodology? I'm going to repeat what I said very briefly at the beginning and try to incarnate it a little bit more. So once again, when you have n particles living in this kind of framework dynamical system, which is, I didn't put, again, the equation for phi, but what you have is vector field, basically. And you look at trajectory, you are in the framework of Lagrangian. That is, Lagrange look at trajectories. And if you look at how a density is pushed, or pushed forward, as we say in mathematics, by this trajectory, this flow, also, once again, if you have things like this, since your system is not Markovian, you don't have a flow, you have just a mapping, but you cannot compose two mappings and saying that the mapping at time t composed with the mapping at time s is equal to the mapping at time t plus s, which is a condition to have a flow. So you don't need to have a flow, in fact. You look at a probability on your full phase space, and this probability is a probability that if you pick up one particle, it is at the position corresponding to the index I. And of course, all the possibilities are given by this probability. And this probability is propagated by the Liouville equation, which is the equation that satisfies the push forward. Let's forget about the forward. Pushing is the density at time t equals 0, and looking at what happens at time t. I'm supposed to finish? This is where you stand?
No,
okay, fine. Okay.
Tell me, what is phi there?
So phi is, phi is the mapping which to xi vi, all the xi at time t equals 0, send these quantities to the same at time t.
No, this
That's a flow. Ah, sorry.
You have grad x phi t.
Ah, so phi t is a potential which takes care of the chemical interaction, that is, which is given by a no, this is good that I remind you. It's given by, it solves a parabolic equation involving the trajectories itself. So it's really a true coupling, you know. The trajectory depends on the chemical potential, which depends on the trajectory. And this is a subtle couple. It's not an explicit couple. Yeah. Also, okay. So once again, this flow, like every flow, even if it's not a flow, it becomes untractable when n tends to infinity, because you are going to have, even if it was linear, you have matrix. When n gets to the infinity, it's like passing from quantum mechanics to quantum field theory. I say that just to take the attention. No, it doesn't work. Okay, fine. Of Olga. Anyway, so it's completely untractable. So you have to find something in order to handle this limit when n goes to infinity. And this will be given by the none but one expression I was mentioning at the beginning, and which is associated to the name of marginal. So suppose you have a density as we have in all the variables as we had before, you know, this one. And suppose that I take the integral of this with respect to all the variables, x2, xn, except the first one that I call now x and v, because they are really particularized. So not x1, v1, I call them x and v, because that's the one I choose. Of course, you see, if all the particle, if the rho is invariant by permutation of all the particles, of course, this quantity doesn't depend on the one you don't integrate over, of course. So it's the same for whatever you pick up. You could keep up x30 here. It would give you the same thing. So there are two facts, and the first fact was, which once again I emphasize, because I think it's not done so often, but is the fact that although a density rho n like this has no meaning if you put n equal infinity, because you should have function on infinite space, you can do it, but you can do it with so many constraints and restriction, topological constraints, that it's not at all what is going to be useful for you. But this quantity now, which is a function of only one variable, xv, this one has a limit when n goes to infinity. So you see, this means that your system, your dynamical system, is become completely crazy when n tends to infinity, ergodic or not, as mentioned Mario yesterday. But if you neglect all the particle but one, this has a limit when the number of particles over which that you neglect, that is, you remove all information about it because you integrate over them, this has a limit. And moreover, this function satisfied an equation, and this equation is the following. It's named to that of equation. And here, pub, for quantum theory, in fact, one usually says that quantum follows classical, but it's not true. The equivalent of that, there is a formalization of this in quantum mechanics. This was done by Hartree. I think it's 1929 or 31, I don't remember exactly. That is 2 or 3 years after the Schrödinger equation. And it was before the Vlasov equation. Quantum 1 point. But of course, it was totally independent. I'm not saying that Vlasov derived his equation by knowing Hartree. One Saturday afternoon, where you have to have fun, look at the paper by Hartree. It's fascinating. Hartree was not a mathematician, he was not a physicist, he was an engineer. And the way he wrote his paper is absolutely fantastic. He doesn't even write the equation. And the name, the name of Hartree is one of the most quoted names in science since it was. It's absolutely superb to see how the uncorrelation, the unconnection between the way you write paper and the way you quote it after. I'm not saying that for young people who should try to write very bad papers, of course, but sometimes it works. Okay, so what is this Vlasov equation that satisfies your first marginal? Also, I'm talking about marginals only marginals here, but in fact this is called the first marginal because you integrate over n minus 1. But you see you could fix x1 and x2, integrate only over x3, xn, v3, vn. So this would be called the second marginal. And everything works the same basically with all the marginal, but of course not when you take as many particles you don't neglect to the number of particles you neglect, because then you have a conflict. And this is a long story on which we worked a lot with Mario and Sergio Simonella to see how far you can take in the order of marginals. But that's a totally different subject. So I didn't write on purpose the Liouville equation, because anyway we forget it immediately. But what is the Vlasov equation? You see, when you take only this part, this is the kinetic part, and if it was not the second part, then the solution here would be given by the fact that you push forward this on the flow x plus t v, because it's very easy that the derivative with respect to t give you a v outside, and this would satisfy this. So this is exactly the part which is propagated by the free evolution. That is an evolution where you have the Hamiltonian, which consists only that is the first part of the equation in the system of the Newton law. And then you have something like this, which handle now the derivative with respect to v, that is which take care about propagation in the v variable. This takes care about propagation in the x variable. This is why you have a derivative of x. Sorry for people who are not very differential taste, but if you look at this just by writing chain rule, it's heavy. So you have something which is like this. It's like you derive this by rho, and then you have a factor here. And the new thing now, just forget about this for the moment. The new thing now is that this vector field, that is this which propagates in a variable v, depends on rho itself. This is a big novelty with respect to Liouville equation. In the Liouville equation, which lives on a huge space, you don't have dependence on the solution in the way you propagate on v. In Vlasov, you reduce to one particle, but the equation, the dynamics, depends on the solution itself. So this is a
psi in the second equation is the phi of the first. What is the coupling between the two?
That's this one. You know, this was your two-body interaction.
I mean, what is phi in the first equation?
Here, this one. This one.
Second.
And the second one.
You mean you? This phi. Yeah, and so first of all, I didn't get to this point yet, because I suppose we are neglecting this.
I don't see how they are coupled.
So this, so now if you add this is a very simple thing in the sense that in principle it doesn't depend like this one on rho, but it does depend on rho because it solves an equation which depends on all the history of rho s from t equals 0 to t. So, I'm sorry. This is, yeah. Okay, sorry. You have to change, we have to change H to S. Yeah, to S to H, yeah. So, thank you very much. No, this is phi, sorry. This is phi, right? And the same phi that you have here, okay. Yeah, so now I understand what the problem is. So this kind of derivation without this kind of thing go back to the beginning of the universe, basically, but it was formalized in mathematics in a very nice paper by Alain Solschnitzmann, and we did also with François Goltz and Clément Mouot give a derivation very precise and with estimation of the constant and all that for the marginal in a paper a few years ago. Okay, so this means that in fact, you see, you have here an equation involving self-interaction of the density by itself, because this is quadratic in the density. And this means that the dynamics that you have on your phase space now is a dynamics which involve also the density. This means that the trajectory is not given just by the initial condition that you push forward, but it depends also on another parameter, which was the probability itself at time t equals 0. This means that now you phase space, which usually is only these two factors here, now you have an extended phase space which depends also of density of initial conditions. So this is something which exactly fit in the way that this is a phase space as any other phase space. If you take the definition of what is a phase space in Vladimir Arnold's book, you have that the phase space is a space of all the parameters describing your system. And now your system, given by Vlasov equation, you need absolutely to have also a density. I put C infinite, it could be just a measure, probability measure here. You have your density at time t equals 0. Give me a density, give me an initial condition, and then I give you the trajectory here. Okay. Okay, so now let me briefly tell you that, and I think I'm going to... Yeah, okay, and then I will give you two theorems, and then we wait for the... we will go to the coffee break. So you know here I have a function of two variables. And out of this function of two variables, I can give you two functions of only one variable. That is the integral over v, neglecting the velocity. That is, you just have the density, which just forget about the velocity. And then you have this, which is what's called velocity field. That is, you take the average of the variable v with respect to your density. That is the expectation value of your velocity with respect to this density. So why you do that? Well, because usually having two functions of one variable is much simpler than having one function of two variables. This is true numerically. I think Marta will talk about that. But this is true also for yourself. No, that's the contrary. For yourself, it's not obvious that a function of two variables is more complicated than two functions in one variable. Of course, if you think about it, you find it. But it is true. So, if you look now at this quantity, you have a guess that this quantity, or mu and u, should satisfy a closed system of equations that I write it, but I ask you not to look at it because it's not important. The point now, it's not what is the equation itself. It's the fact that two densities like this can satisfy a closed system of equations. It's not true in general because you see, rho was satisfying a closed equation, if you forget the chemics, and but this doesn't mean that the integral over v and the integral of v, rho v, satisfies also a system of equations. Because if you take the Vlasov equation here, you know, if you multiply the solution by v and integrate, it will depend on everything, on other things than two. But it's true that you get a system like this for these two quantities. You know, if you get something like this, you're happy because at least when you talk to non-mathematicians, at least you give them functions on the physical space. You have two functions now, but people like very much two functions on the physical space instead of imagining a phase space which involves, not even talking about the dependencies of density, which involve a velocity that you don't see. You don't see the velocity, you see only positions. So people are happy if you give them this. I mean, some people are happy, and there are people who are never happy anyway, so you shouldn't even try to do anything. But you might answering when it is true that these two quantities satisfy an equation, closed equations themselves. What I mean by closed equations is that the equation involving only mu and u. In fact, the general fact is that the equation will satisfy all the other integrals. That is the integral of v2, the integral of v3, and all that. You have a hierarchy of equations that is very well known. And it is true in two cases, at least. In the case where you have an initial condition which is called monokinetic, which tells you that in fact, at the origin, your velocity fields depend only on the position. I'm just saying that because I'm not going to talk about that. But when you look at, and in a more general situation, is maybe true, but I think, Marta, you're talking about, right? If you have Cooker-Smell things, it's a numerical situation where you see that sometimes you have your two equations which are almost satisfied by this. Okay, in the case where you have multi-agent system, where you name the things, let me tell you what the strategy is, because I'm still in my overview, basically, or my strategy part, and then I will give you theorem. I remember you that an adjoint system is a system of numbers, Ci, from I equal 1 to n, which satisfies an equation like this, where once again, the dynamics depends on the indices. Now, sometimes, of course, this is a matrix, and you're very happy if this matrix is just a discretization of a certain function. So, in the case where you have that this quantity here is in fact a discretization of a given function, it's just an ansatz on the function g ij of xi, xj, then the trick is to consider the index itself, and there is something very tricky and very funny. You will consider the indices as a dynamical system, as a dynamical variable. But a dynamical variable whose solution is constant with respect to time. So you're telling me it's just, it's just magic. It's completely stupid. You say that it's a dynamical system, and then you impose that the dynamical system doesn't move. But it's not true, because in fact, I will show you the theorem after, it gives you a huge kind of degeneralization of the system, which are exactly what you want. So, it seems that I give you and I take it back, but in fact, in the middle, where I give you, before I take it back, you have a lot of zoology which are very helpful. And what you get this way is that the Euler system you had, so it was an Euler system with derivative first of mu, and this disappears just because the dynamical system you added are just not moving, and you got just an equation, and this is called graph limit equation of your system of adjoint system. But I will be more precise on this, much more precise. Okay, 59 theorems. Okay, so theorems. This is a musical allusion. Everybody who can tell me what it makes reference to will win one piece of chocolate. Okay, so in order to, when I pronounce the magic word in mathematics of limit, so when you say that we have a limit, you have to define the topology, that is in which sense the limit exists, that is, you have to define a distance at least on which thing. So the distance which we work for all these kinds of situation, I mean the one I mentioned and some other ones, is associated to the name of Wasserstein. So I'm very rough. Once again, Wasserstein, Kantorowicz is a huge set of names. Is it a distance? Is it not a distance? I mean, it's a distance certainly. Does it involve some higher topology? I'm very rough, and this is a definition. So you take two measures. Measure can be a function integrable, positive function integrable, if you don't want to consider measures. And the square of the distance between mu and nu is going to be this strange object. So what you are going to do is to sum over, to integrate of the square of the Euclidean distance between 2 points, one in each point in Rm. So you will have this distance between points, and you will integrate against another measure. So once again, this could be a rho of x, gamma of x and y dx dy, if the measure is Lebesgue continuous, but I don't want to enter into this. And this is a set of probability measures which are called couplings of this. And what is a coupling of two measures, mu and nu? If you remember the definition of marginals, a coupling of two measures of two, let me put it in function. You have two functions, mu and nu. A coupling between mu and nu is a function of the double number of variables on which, when you integrate over one of the two variables, you get the first measure. If you integrate over the first of the variable, you get the second mu. So what do I mean by this? I should write it, sorry. So what is a coupling of mu and nu considered as a function? So this is a function of y, this is a function of x. This is a function gamma of x and y in such a way that if I integrate over the second variable, I get the first function phi of x, and if I integrate first variable, you know, if I integrate over the first variable, I get a function of the second one, and this is a second nu of y. It's not a very natural object. It's a little bit complicated. For example, it's not so easy to prove that it is a distance. You don't see it immediately. You see, I recall you that the axiomatic of a distance, of the definition of a distance, it has to separate points. At least it has to be symmetric in the two ingredient, mu and nu. That's true because you can see it very quickly. It has to separate points. That is, it has to tell you that W of 2 of mu and mu is equal to 0 only if and only if mu is equal to mu. Sorry, W2 of mu and nu is equal to 0 if and only if mu is equal to nu. This is okay to prove, not completely easy, but what's the difficulty is that the third axiom, that is a triangular inequality, I just want it like this, that it tells you that W of mu nu is smaller than W of mu with respect to rho plus W of rho with respect and nu, triangular inequality. This is really a nightmare to prove. It involves quite sophisticated measure theory of to disintegrate measure. It's not so easy. About all that, basically 4,000 pages by Cédric Villani. You could take any of the two books he wrote. You have everything inside and much more. Okay. Now you can forget about this definition, which is complicated, and says that you have a distance which measure how far away are two measures or two functions. For some result, I will need W1, and W1 is exactly the same definition. You replace the 2 by 1 here, and you replace this 2 by 1 also. But once again, the definition is quite okay, and you don't have to see exactly. So this is to remind you what was the situation where you had a particle system. I just need, I cannot avoid to have a notation for the set of vectors, I mean the set of n particle points, that is, this is a point in R dn times R dn. This is equation I wrote already. This is a coupling with the chemics, etc., etc. This is a Vlasov equation I was talking about. So there are very few times, so no time to detail the equation. Just I remember that I promised you that the first marginal of the push forward initial condition by the flow was going to satisfy the Vlasov equation, and the theorem is the following. So if it was no chemistry, so without this term, this was proven with this exactly this kind of preciseness in the paper by François Gauss, Clément Moreau, and myself, I quoted before, but with the chemical interactions as proved by Roberto Natalini and myself 2 or 3 years ago. And what it tells you is that, so once again, you take a density of n particles, which has the property of being the tensorial product, the tensorial power of a single one, which means that you take a density which is invariant by all permutations, but not all of them, only the one which are the same density for each particle, and you glue them together. You push by the flow, and you take the first marginal. That's a notation for taking the first marginal. So this is one particle density, in the sense that it depends on the variable of one particle. And you compare this to the solution of the Vlasov equation, which start with this function here. I'm sorry, it's a little bit complicated. And you get something which decreases when n goes to infinity as a low power. Then you have also a result for the equation, which is kind of probability result, I mean something like it expected for almost all the Zn. But I will not describe this because I'm really late already, and it's a little bit complicated to explain. The important fact is this one. You compare in this topology the distance of this object, which I told you were tending to this one, and it tends in the fact that the Wasserstein distance between the two decreases when n tends to infinity. The second theorem was the theorem involving the density of velocity and the velocity field and the density of velocity. This was the horrible equation. I didn't want to show you so much. And it tells you that if you have a solution of this, then this monokinetic stuff, once again, I'm just saying some words and not explaining, solves the Vlasov equation. This is something I don't want to see. So this is a diagram we have telling you that here you have particle system, here you have a layer, you pass through Vlasov, it will, but I don't want you to watch too much on this because it's too complicated. I took this trick from Peter Lax, you know. He will show you equation for 10 seconds and he erases it. This creates big frustration in people who agree. I will show you more at the end, don't worry. So, numerical intermezzo. I think I leave that because Marta is going to talk about that. Am I right, Marta? Yes? Okay, so I skip this. I was planning to tell you this in case Marta wouldn't come, but she came, very good. And now I would like to concentrate the last 15 minutes I have or so, 18 minutes I have, on the agent system because it's something that I can show you more things with figures, hopefully. So let me remind you that an agent system is a set of equations telling you that the time derivative of the variable ci, and I is equal from 1 to n, is a sum of this type of function which depends non-linearly a priori of all the variables, and a sum of over a function which depends on indices g and j. So once again, you have that the derivative of Francesco is equal to a certain interaction between Francesco and Mario. And this interaction depends on the fact that you have Mario and Francesco. This, in fact, covers all the system I talked to you before, because just the Hamiltonian system, for example, Cooker-Smell system, in the case where the matrix here, I mean the function here, doesn't depend on A and J. So anything you prove for this is valid for the other system. And in particular, for this one, where you depend on A and J, and this is a kind of emblematic opinion system. Alors, fundamental remark and trick. Usually, when you have no dependency here, you preserve indistinguishability. That's the first time I say it so easily, so I won't say it again. It preserves this stereo word. That is, when you exchange particles, it doesn't change the dynamics. For opinion system, it does. And this means that you need some kind of new method to handle the system. And the kind of new paradigm will be, once again, to define the indices here, E and J, as some dynamical system. So this should be an A of t, J of t, but I call X and Xi and Xj in order to make them more like dynamical variables, but they don't move. The derivative with respect to time is equal to 0. And once again, it seems that you didn't do so well, but you did a lot of things. And I will suppose that this is the discretization of a certain function. So in a certain sense, xi of t or xi will be an I over n. This means that n will be the path of discretization. Okay. So usually what people do in opinion system is that they look at an equation like this, and you know, this looks very much like a Riemann sum, in fact. I recall you that when you compute the integral of a function in the Riemann theory, you discretize your continuous variable by some points which are like I over n, and instead of having an integral, I mean, you define the integral as the sum of the value of the function evaluated at all these points, discrete points, and you take when the discrete points become continuous, that is the limit when n goes to infinity. So this looks like a Riemann function, but the goal is to handle this where G, which are not a priori the regularity that need a function to have a Riemann integral, which is the limit of the sum of its discretization. So it's a big work which has been done by several people. In fact, I quoted in the overview And sorry, there is something missing here. I didn't got. But anyway, the important fact is that if you consider this way a way of handling this term by discretization, this means that the variable ci of t, you will consider that it's a discretization of a given function itself. And anyway, by this, you associate it one opinion to each agent. The agent I, Francesco, Mario, has the opinion, which is xi y of I of n. Usually opposite, but they have just one opinion each, they don't change of opinion. If you remember that I told you that what I presented in the first part was associated to kind of evolution of probability theory, if you try to do the same, and I'll do it, this means that in fact now to each agent you will associate a random variable given by this probability like this. And it seems to us is Emmanuel Trella and myself, that it's more natural in a certain sense, because people in general, I mean, in social science, they don't have a given opinion. They have a probability of opinion, and they fix their opinion at the end. So if you do the kind of algorithm I propose you have an average over all but on adjacent and hydrodynamic, and this will give you at the end the same equation that the one you get by considering a Riemann integral of this. This is a little bit obscure, but anyway. You have a Vlasov equation, exactly like we had before, because now you know we are considering that instead of having a dependence on the dynamics on A and J, you have some extra variable, this one and this one, that I call, sorry, this is a mistake, this should be xi and this should be xj, extra variable, and then you can perform and say, I do exactly as before. It's happened that the equation for xi is this one, the derivative with respect to time is equal to 0. In a certain sense, this corresponds, if you remember that in principle, when you pass from Newton's law to velocity and position, you have the mass of the particle, which is important. And if you get 0 here, this is corresponding to let the mass of your particle tending to 0, so everything is consistent, basically. You have a Vlasov equation, which is the same, and I don't comment it because we don't have time. And the point is that you want to have an initial condition which do the job, and the initial condition consists, you know, of fixing all the xi into I over n through a delta function here. I'm trying to get fast, I don't know, I think it's going to be not very understandable, but still, I go, and what you find is that the same formulation as we had before, but this time with W1 for some technical reason, and you get something like this with a remainder with other n. Suppose that k is equal to 1 here. And so you have convergence again of the pushing forward of this quantity by the flow given by the equation here, and the solution of the Vlasov equation, which is here, and the distance in W1 topology this time tends to 0. So basically it's come prima, as before.
In the estimate, K is...
So yeah, sorry. So suppose K is equal to 1, but K is the order of the marginal, in fact, sorry. That is the marginal, that is, it's not valid if you take the marginal that is neglecting all the agent but 1, but you can neglect n minus k agent but k1. And you see this formula, you see that, for example, if k is equal to 1, exponential 1 over n minus n is over the 1 over n. It's valid for Lk, but if k is equal to square root of n, then you have exponential which is not close to 1. So this means that you can neglect all, this is a general philosophy, in fact, in a general result, you can neglect all the particle or the agent, but square root of n maximum. I mean, even less, strictly less than square root of n. There is a threshold in the fact that all the theory breaks down when you don't neglect enough agents of your system. You really have to pay a lot on the fact of neglecting agent of particles. Okay, so this is what is written here. Okay, So this is why I told you if you do all the paths, but I'm going to be quick on that because I realize that it will need some too much time to do this. This is the schema which again I don't show you so much because I want to get to this point and to very briefly describe what's happening. If now you suppose that you have the equation limiting and you look at the system of agent, will give you this limiting equation that you wanted. Alors, if you have some agent system, you get a graph limit equation, that is the Euler equation, but the Euler equation as a property is a conservation law in this formula, that it is a first order differential equation. So if you just take normal system of agent, you will get only first order differential equation, and you would like to get any kind, or at least general classes of partial differential equation. And to do that, what you do is that you take a generator of your dynamics which becomes singular. You add a parameter epsilon, and you suppose you see this is a horrible notation, but this is a derivative or an approximation of the delta function. So when epsilon goes to 0, it tends to something which is not anymore a function, and that is which is a distribution. So this means that if you take an agent system with something like this, you fix n, you let epsilon goes to 0, you get something which is not defined, absolutely not defined, because you'd get a system of equation with a distribution inside, and this is extremely singular. I don't say more than this. But if you take together the limit when n tends to infinity and epsilon tends to 0 together, for example, taking n infinity and epsilon is equal to 1 over the logarithm of the logarithm of n, we have to be in epsilon is equal to 1 of log n, then you get a differential equation of higher order here. So the scheme now is the following. You added the parameter epsilon, you have a particle system, and this is when epsilon goes to 0. I mean, this is like a modification of your partial differentiation driven by the parameter epsilon. And what governs this limit is something with a double exponential in epsilon, which explains the double log in what I just said now. As if you have this part is perfectly under control, but now you have to compare what is a modification of a differential equation is one that, you know, when you have a differential equation, you have a differential operator. This differential operator, you can see it as an operator, an integral kernel with an integral kernel, which is a distribution, the delta function, the derivative of the delta function also. If instead of the delta function, you approximate it by a Gaussian, as we know how to do, this gives you what we call a modification. And the big problem is to look how this, we thought it was very simple, but it's not at all simple, how a modification in this sense of a partial differential equation tends to a partial differential equation. I should drink something. And this is basically my last transparent. Since we are mathematicians, we put everything on generality like this, but don't read it. Instead of having a general PDE like this, and for the moment, we know only how to do a linear partial differential equation, but we have some hints to go to at least quasi-linear partial differential equation. And what you get is that in this strong topology, you build out of your system like this a function which will tend. That is, you have an approximation of your linear PDE by what's the result of a particle system. So this is the other way. You approximate micro by micro, as the contrary of approximating micro when n tends to infinity with respect to macro. So this was just to indicate things, just a program of what you can do. This was really for specialists. So I forget about that. And finally, I leave you with this apocalyptic diagram, and I'm finished. mean, I've answered.
Questions?
5 minutes.
Your last slide, the idea of estimating PDE by micro.
Yeah.
Does it have any relation with the more standard approximation of PDEs?
That we don't know.
The difference?
Discretization, lax theory, and yeah.
Factor or
The point, I mean, the interest of, we believe, what we did is that you don't have to prove, it works automatically. We don't have to, you know, when you do the lax condition for the discretization, all that, here is automatically satisfied. So it's in fact very far away to the discretization of the PDE. It's very far away. So it works, but it works only for special PDE, and but at least you have something which is canonical in a certain sense. You know, you give me your PDE, I give you a system of particles, and you turn the manual and it gives you nothing else to prove.
anyone has done
Yeah.
simulation of this?
No, not yet.
Well, there is may I comment? There is an organization called the mesh-free particle approximation. They are doing a numerical analysis with a particle system, nothing to do with our particle.
That's different.
It's something ad hoc for numerical simulation.
I'm not sure there is nothing to do. We
Well,
should investigate.
yeah, that's another
There is a
problem.
relationship.
But there is this mesh-free methods that are particle methods, numerical analysis.
You have an algorithm given the partial differential equation to get the particle system.
No, it's explicit. The particle system is explicit in terms of the PDE.
And which family of partial differential equations?
So you need, we're quite sure it will work for any quasi-linear equation, which has a semigroup property of the solution.
Which has?
Whose solution is given by a semigroup. You know, that is, which is a dissipative equation. You know, in the formalism of, I don't remember who. So you have a condition that you have this, but
you know, I'm strongly interested in that, but we will need to talk.